Hello, and welcome to our video on acid-base reactions, as well as titration. So we're going to begin by talking about neutralization reactions, but before we even get quite to that, we should talk about identifying acids and bases. We mentioned in a previous video, it's pretty easy to identify acids. Acids will have the hydrogen listed first in the formula, so that's one giveaway. Or if you're given the name, you can look and see that they usually have acid in the name. So hydrofluoric acid, nitric acid, so on and so forth. So again, if it has acid in the name or starts with hydrogen, you can be pretty certain that it's an acid. The bases are much trickier. So how do we identify the bases? Well, we don't really have a good way to do that yet. We don't have the tools for that. So I've picked out 4 really common bases that I'd like you to memorize. And those 4 really common bases are hydroxide, bicarbonate, carbonate, and ammonia. And so I picked these ones not only because they're common in chemistry, but they're also, all 4 of them, very important in biological systems as well. So just a heads up there, you want to memorize these 4 bases. So if you see compounds containing any one of these 4 bases, then you know that that compound is going to be basic. And so I've created some acid-base reactions here, and we're probably the best way to do this is just to go on to the next page and do some example problems. So here is the type of thing you might be asked. Write the balanced neutralization equation for magnesium hydroxide and nitric acid. So here is what you'd be given in a quiz or exam question. So you have your magnesium hydroxide and your nitric acid. And the first thing we want to do is identify which base we have. So if we go back to the previous slide here, I see, oh, one of our bases is hydroxide. And so we have hydroxide ions present here. And not only do we have one hydroxide, we have 2 hydroxides. So going back to our previous slide, I see that 1 proton plus 1 hydroxide is going to produce 1 water molecule. So over here, if we have 2 hydroxides, we are going to need 2 protons. That's going to require 2 nitric acids. So that's going to give us our 2 protons. And then we're going to make 2 H2O as a product of this reaction. So there we go, there's our 2 H2O. Apologize for my handwriting, it's a little hard with the mouse, but there's our 2 H2O. But we also have some other things present here. We have some magnesium ions, so there's our magnesium. And those are going to couple with our nitrates in order to form magnesium nitrate. And there's going to be 2 of those. I'm going to drop down below because I'm a little bit out of space right here. The state for the magnesium nitrate is going to be aqueous. So there is our not very pretty, but hopefully legible reaction between these 2 materials. We would take 1 magnesium hydroxide to react with 2 nitric acids to produce 2 H2Os and a magnesium nitrate. So if we look at another example right here, we want to write the balanced chemical equation for the reaction of magnesium carbonate with HCl. Now if we go back to the previous slide here, we see, oh, our base in this case is carbonate, because we have carbonate ions present. And therefore this is the reaction we're going to use. 1 carbonate reacts with 2 protons to make 2 H2Os and 2 CO2s. So looking at our reaction here, we have 1 carbonate. So that means that we would require 2 HCl's to neutralize that 1 carbonate. And that 1 carbonate plus 2 protons is going to make both a single H2O as well as a single CO2. And again, I apologize for my handwriting, but hopefully it's legible. And then from there, we're going to have also our leftover ions of our magnesiums and our chlorines. And in this case, that'd be aqueous. So I want to point out that these reactions are generally going to produce water, sometimes CO2 if we have carbonate or bicarbonate, as well as some sort of ionic compound. And people sometimes call these ionic compounds salts. So just a heads up there, in chemistry that term salt and ionic compound are kind of interchangeable terms. So I'd like you to pause the video and please complete questions 1 and 2. Alright, welcome back. Let's move on to our final topic, which is acid-base titration. So this is a method people use oftentimes to find out the concentration of a solution. And so if you haven't done it already, in lab you're going to be using a base in order to titrate an acid and find the concentration of that acid. So this is the type of stoichiometry problem. So this is going to take some of the chapters, some of the stuff from the stoichiometry chapter, some of the stuff from the solutions chapter, as well as some of our acid-base stuff, and combine it all together. And so a titration setup, we use a piece of glassware known as a burette. And so here's our burette right here. We're going to put, in this case, and in the case of the lab we'll be doing, our base in there. Then we're going to have our acid solution down below. So here's our acid in a Erlenmeyer flask, and in this case, and then we have our base in the burette. And so what we're going to do is we're going to add an indicator to this solution and down in our Erlenmeyer flask. So what is an indicator? Well, it's exactly what the name implies. It's something that's going to indicate when the acidity or basicity of the solution changes. And so the indicator that's shown in the picture is the same one we'll be using in the titration lab. It's called phenolphthalein. And so what happens is that it reacts with the base and it turns kind of pink purple in color. And what you see is it's going to form this sort of splash of pink purple, or some people call it violet, and that's going to disappear pretty quickly as the neutralization reaction occurs. But eventually, if we keep adding it, we're going to reach this point where we have this sort of faint pink or faint purple color that's going to stay indefinitely and spread throughout the solution. And so our goal in a titration experiment is to figure out, like, to the exact drop, how much base is required in this case to get the solution to change color. And so once we have that data, we can do some stoichiometry calculations. And so here's the type of problem you might see. And these calculations actually might be quite helpful in terms of preparing your lab report for the titration lab if you haven't done the titration lab already. So our question here is, what is the molarity of HCl if 18.5 milliliters of a 0.225 molar solution of NaOH are required to neutralize 10 milliliters of HCl? So first thing we need is a balanced equation. This one's pretty simple to balance. Everything's in a 1-to-1-to-1 ratio. Then we're going to start with our volume of the thing we know the concentration of. So here's our 18.5 milliliters. We're going to plug it into our equation here. You'll notice that it's been converted to liters. Why is it converted to liters? So we can cancel it out with our molarity right here. So our liters are going to cancel. And so here's our concentration. That was given in the problem as well. Boom, so that goes right here. And then we're going to use our balanced chemical equation. We can see that our HCl and NaOH react in a 1-to-1 ratio, so that's going to go right here. And our moles of NaOH are going to cancel. We're left with moles of HCl. And we're going to take our answer, our moles of HCl, and divide it by our volume. So we're going to take this value here, convert it to liters, and divide. And so then we end up with 0.416 moles per liter of HCl. So you'll be doing very similar calculations, different balanced equation, different numbers and stuff in that lab if you haven't done it already. So please pause the video and, please end the video and complete questions 3 through 6. Thanks.